So today is this morning is the third lecture in the Proof Theory Foundations sequence of lectures. So I'm going to talk about verifications, and I'll explain what that is. Then we'll talk about sequent calculus. And at the end of the lecture, we'll have all the tools in place, so we should be able to prove that certain things cannot be proved, right? That was the question. How do we know that we really cannot prove A or not A in general, for example, or that it's not the case that one of these interaction laws holds that we were postulating? Okay, so we already kind of decided in the proof theoretic approach to think about logics that the meaning of a connective is given by its introduction rules, right? That was kind of one of our basic things. Now, the next question is, what is the meaning of a proposition? The meaning of a okay. So we kind of already fixed what's supposed to be the meaning of the connectives by giving the definition by the rules. But what does a proposition actually mean, right? So it's now composed of a bunch of connectives, like implication at the top and conjunctions, disjunctions, and so on underneath, right? What's the meaning of that? Okay. Anybody want to speak to that question? Yeah? Okay, so it should be the collection of all the evidence for it being true. In other words, it's sort of given by the totality of its proofs, maybe. Okay? Now that, unfortunately, is a very problematic notion. Okay? And that's for the following reason. Okay? You want the meaning of a proposition only depend on the meaning of its parts. Okay? So you don't want to have to go outside the proposition that you're analyzing to define what its meaning is, right? So you want some kind of compositionality, or you want some kind of you want to be able to look at a proposition, you want to be able to see its meaning, okay, without looking outside for other things. And the problem is that when you're trying to find the meaning of a proposition A, and it's defined by all of its proofs, okay, then unfortunately there are proofs that look like this. And so in order to understand what A means, okay, you would also have to understand what B means, right? But B could be a much larger proposition, so you haven't really broken down the problem of understanding the meaning of the proposition. So we cannot take all possible proofs. That's too much, right? Because that's sort of not a well-founded way to try to understand what a proposition means. Okay. So what we want to do, well, anybody have a suggestion how we can get around this problem that, you know, we cannot count all possible proofs? Okay, take the smallest. So we would need to define smallest, so that's not really quite the right thing. Also, sometimes, you know, you need to look at more than one possible proof in order to really understand what it means, because that may not be sort of the canonical way of proving it. Okay. Yeah? That's a very good thought. So let's not use elimination rules, right? Because we define the meaning of a connective by its introduction rules, right? And so if you have a large proposition, why don't we just decompose it by the introduction rules, not use eliminations? We should get the meaning of it, right? Now, unfortunately, that doesn't work, because how do you explain the meaning of something like A implies B implies C implies that A and B implies C, because we already know there's no way to prove that without using elimination rules, right? So therefore, in this definition, if you stick to that strictly, there would be no proof for it, no meaning for it, right? So we have to use eliminations as well. But we cannot use them some kind of arbitrary way. Any other thoughts on how we might get around this problem? Okay, so maybe going back, maybe we could make a following restriction. Maybe we could take the totality, so the totality of all proofs that just decompose the propositions but don't depend on anything else. Okay? So you're not allowed to do something like this if you're trying to prove A, okay, in the proof because B is arbitrary. So we just want to decompose the proposition that we're trying to prove. Okay? So another way to say that would be it would be determined by the proofs which have a subformular property, that everything that occurs in the proof is a subformula of what we're trying to prove, right? So that eliminates at least this kind of problem, okay? Because we don't have to refer to externally. But that doesn't seem to match very well with the idea that the meaning of the connectives is given by the introduction rules, okay? Okay, so what we're going to say is we're going to define a new notion, okay? And we call that notion of verification. And the idea will be that we define it in such a way that it's okay to say the meaning of a proposition is given by all possible verifications of it. Okay? All right, so we'll start with the easy one. Okay, so we're actually going to write it like this. A up arrow, it's a new judgment mean A has a verification. Okay. And the idea is that verifications are the subsets of all possible proofs, right? Somehow you want to restrict it to proofs that have certain specific properties that are correct so that we can think of a verification as determining the meaning of a proposition. Okay. So if we start with that, okay, how would we think of a verification of A and B? Okay. What would be a candidate for verifications of A and B? It's compositional because we break down into the pieces, okay, and we say A and B has a verification if A and B both have verifications. And in fact, if you don't mind overloading names, we can even call that the end introduction rule. Okay? But it's slightly different from before because we're now talking about a different judgment. We're trying to characterize only the verifications. Okay. Okay, so this is a good start, right? So the meaning of A and B, where A and B is arbitrary propositions, can be understood as a combination of the meanings of A and B. So that's a good part. Okay, so we have a problem with the AND elimination rule at the moment, right? Because if we think about AND elimination, it looks like this. Okay? So it would be wrong to say we have a verification of A if we have a verification of A and B, right? That goes the wrong direction because we're not breaking down this proposition. Okay? So that is exactly what we wanted to avoid, introducing something that we don't already know. Okay. So in order to see how to resolve that, let's think about how we define the meaning, the verification of an implication. A implies B. Okay, so what would be a verification? What might count as a verification of that? Okay. So there's a verification. Given a verification of A, let's call this X. Okay, so that might be the first attempt. Okay, the problem now is that we have this assumption A up here that we can actually use. We're not actually ever going to fill in a verification of that because that's an assumption, right? And the verifications always go like bottom up. We use introduction rules with verifications. So if you have an assumption, what do we actually do with assumptions? I mean, you have constructed some proof in the exercises, so you have some kind of an idea. What do we do with assumptions? We apply elimination rules to them, right? And at the end, they have to be discharged, right? But we reason downwards them by using elimination rules, right? So if we know A and B, then we can deduce A. Okay. So we're reasoning downwards by elimination rules from the things that we know and upwards by introduction rules from the things that we're trying to prove, right? So rather than saying, if you have a verification of A, we get one of B, what we're going to say is, we must have a verification here of B where we're allowed to use A. Okay? We're allowed to break down A by using elimination rules applied to them. Okay? So that's the second judgment we need. A down means A may be used. Okay. So to get a verification of A implies B, we give ourselves license to use A, and we try to get a verification of B. Okay. So now, with that in mind, can we come back to that? So how would we think about that rule now? How would we think about that rule?
A and B may be used and A.
Right. We may use A and B. We're allowed to use A. Makes sense? Because we're reasoning downwards from our assumption. So that's the first elimination rule. And the second one, of course, would be if you can use A and B, then we're allowed to use B. Okay. So the general picture that we'll have to complete is something like this. Okay. A verification is something that only uses introduction rules going bottom up and only uses elimination rules going top down. Okay. Now, why does this guarantee the property that you only decompose the thing that you're trying to prove? Anybody see why that's the case? Okay, so it's the case because on any of the introduction rules, if you read them in this direction, right, eliminate that connective, or if you read it top down, they introduce it, but if you think it bottom up, you get rid of that connective, right? So the premises of the introduction rule only contain pieces of what you're trying to prove, right? And the conclusion of the elimination rule only contain pieces of what you assumed. So therefore, you only ever generate subformulas of what you already have when you start, right? Because you extract subformulas from assumptions, and you extract some formula from the conclusions in the two directions, okay? All right, keeping that in mind, what should be the A implies B, the implication elimination rule? Okay, so we can write down the rule because essentially we want the verifications to be a subset of all the possible proofs. So all the rules should be familiar. We're just restricting their use with these new judgments, right? Okay, so how do we annotate this, right? There's three propositions in here, so we have 2 to the 3 different possibilities, right? One of them has to be the right one, okay? Okay, what about A implies B? Down. Right, because the elimination rule is always applied to something that we're allowed to use, that we know we can use, right? That's, okay. Now what about B? Down, because we have extracted it from something that we know, so now we can use B in our proof. What about A? Okay. Because now we have to find some kind of a proof of A in order to eliminate this assumption from here. Okay, there's an interesting sort of connection here. You see, in the introduction rule, A and B is used with an up arrow, so it's used with a down arrow here in the elimination rule. This is with an up arrow, of course, it's a down arrow here. But if you look at the premises, B has an up arrow here, so it has a down arrow here. This has a down arrow here, so the corresponding thing has an up arrow. So when you go from between introduction and elimination rules, because you change your direction, you always flip the arrows. Okay. Okay, so we're not quite done yet. With these rules, we can't really prove very much yet. Okay, so what's missing? Yeah, disjunction. So, but there are some theorems like, you know, the currying and uncurrying laws that you can perfectly well write already in this part of the logic. But we won't be able to prove that. In fact, I even claim we cannot prove at this point that A implies A has a verification. Okay? So how would we prove that? Well, we look at our rules. Okay? Which rules apply? Which of those 5 rules applies to try to find a verification of A implies A? Right, this is the only one that applies, right? Nothing else applies. See, at this point, if we know that every proposition that's true has a verification, okay, we already know something very important, because previously the problem was, for any conclusion, you might have been able to apply the implication elimination rule, right? No matter what you're trying to prove, you can always make up a lemma. Now this is no longer true, because if you're trying to find a verification of it, the conclusion of the implication elimination is a down arrow. Okay. So at this point, we already know if we're looking for a verification, there's only one possibility. Right? It has to be implication introduction. So we're trying to find a verification of A, and we have license to use A. Okay? So now what? Well, we can't use any of these rules because they just break down propositions, but we've already broken it down to basically atomic form. So what do we need to do at this point? Yeah?
Maybe we need like a rule that if you have like, you can use it, like it's separately bring them down to.
Okay, so yeah. Yeah, so if we're allowed to use A, that counts as a verification of A. So this is some kind of a conversion between the two, and then we can use that here. Okay, like that. Okay, now this is now we have created a small problem here, or well, I don't know if you want to call it this problem, but now if you're looking for a proof of A implies A, okay, there's 2 possibilities. You might use the implication introduction rule, or you might try this rule, right? So we have introduced a second possibility, but the meaning of the connectors was given by the introduction rules, okay? So if the meaning of the implication is given by the introduction rule, we shouldn't have to go outside and try to look for some kind of possible use of that. It should always finish, in some sense, with the implication introduction. So what we want to do is we want to restrict this rule, okay, to the point where we have broken down the connective to the atomic pieces. Okay. So we want to make a restriction here that this is an atomic formula which is usually written as P. So P is atomic. So in other words, we've broken it down to one of these variables that we have over there, like A implies A, right? It's one of these A's rather than an implication or conjunction and so on. Okay, so that's what verifications are. Okay, and as I argued before, they should have the subformula property in the sense that you know if you're trying to prove something closed without any assumptions, okay, and you break it down, you're only ever going to use subformulas of what you're trying to prove. Okay. Are there other remarks or questions about this? Yeah?
So it seems like where you're going is trying to have a more structured form that's good for proof search and things like that, and that motivation is clear. But your original motivation was a little grander, like what should be the meaning of a proposition.
Yeah.
And I wasn't sure that I understood the criteria that you were applying to what would be a good answer to that. So the first proposal was, what about the set of all of its proofs?
Right.
And what was wrong with that answer?
Okay. If you take the set of all proofs, then the problem is that if you're trying to find the meaning of A, then because it could have been inferred this way, know the meaning of B.
If you're trying to find the meaning of.
Yeah. If you're trying to see what is the meaning of A.
So it is about proof search in a sense.
It is, but it's also in trying to understand. So if you think about what the meaning of something is, right, you should be able to compose it off its parts rather than having to go outside to something arbitrary. And if you just say the set of all proofs, then any possible proposition may play a role. And particularly if I decide now to introduce universal quantification, I have to revise my idea of what the meaning of a proposition might be, because it could be that B involves universal quantification. So I really want to be able to understand the meaning of a proposition only by looking at its parts. So what I need is a notion that is like a proof, okay, except that it only examines the parts of what I'm looking at, of the proposition. And that's what verifications are. Okay. And they are consistent with what we talked about before, in the sense that we think of the introduction rules as defining it, okay, because the verification of a proposition is always defined by its introduction rules. Okay. Now we also have to refer to the elimination rules, but we justify them, so that's okay. We justified the elimination rules already, so referring to them in the definition of what a verification is okay, because we already know that the elimination rules can be justified from the introduction rules. Okay. Now, the second part of this is a tremendous simplification of the search space, okay, because we have now really reduced the space of possible proofs. So now at this point, if we believe that everything that's true also has a verification, which is something we haven't proved, okay, then we should be able to show that certain things cannot be true. But we can at least say at this point that certain things don't have verifications. Okay. So an example would be if you have, let's see, either I should probably use disjunction in order to give some good examples, because we're talking about excluded middle. Okay. So let me put up disjunction. So what's the verification of A or B? Well, there's a certain things I can write on the chart. Yeah?
That's what we mean, but I mean, we're going for the up arrow, right?
Yeah. So what's the verification of A or B? Two possibilities. It could be verification of A, or it could be verification of B, right? Because that's the two introduction rules. And what's the, let's write down the elimination rule. If we have A or B, and then we have from A, we go to C, from B, we go to C, then we go to C, okay? This is this scope, this has this scope here. So now we just need to put arrows on this. What's the arrow in A or B? Down. That's something I may use. Okay. And then what about this A? It's down. It's something which I can now use in this subproof. B is also something I can use down in this subproof. What about C? Okay. So it's a little unclear. You might think, so it's certainly up to find a verification of C. Okay, we can do this picture. There's also some possibility that down arrow here might work. In order to be allowed to be able to use C, you have to show that you can use it in both cases. Okay. So there's some discussion, there's some homework exercises connected with that, so I don't want to go into more detail. Okay, so now let's take either A or A implies B. Okay, so classically, this is true, right? Classically, you reason as follows. A must be either true or false. If A is true, then this thing holds. If A is false, then it implies everything, so then this part holds. So in either case, either this one or this one holds, so this should be a theorem of classical logic. Okay, very simple. Now in intuitionistic logic, okay, of course this doesn't hold, but let's just see if it has a verification. So what are the possibilities here to start to find a verification? Right, it has to be one of the two or introductions because these are the only possible rules. So it has to be either this, or it has to be A, or A implies B, up arrow, if A implies B has a verification. Now here we're stuck at this point because no rule applies, right? Oh no, wait, no. We can do one more thing, right? Switch the arrow, right? You could say, this is because we allow to use A, but we have no assumption, so we're stuck at this point. Yeah?
or elimination rule there?
Uh,
Is there some special thing about C that we need to write down?
no, we could use the or elimination rule, but we don't have A or B that we can use. So therefore, at this point, we're stuck. That rule doesn't apply because we don't have A or B. Okay. Now here, what can we do here? We have reduced it to that. Our hand is forced to find a verification of A implies B. What are the possibilities? Only one rule applies, right? Okay. So, and that rule says we're allowed to use A while we try to verify B. And this. Okay, how can we use A? Well, there's only one thing we could possibly do with that. We could coerce it, right? Because this is an atomic thing, so we could coerce it to that. What could we do with B? Same thing in the other direction. But in either case, after that, we're stuck, right? And we're finished because after that, we know that, well, A has verification of that, and here we have to prove that B is something we're allowed to use, and we don't have those things. We cannot proceed from there. Okay. So there's no verification of this, which means that it shouldn't be universally true, because we can't verify it for arbitrary A and B. And if we have a theorem that says everything that's true has a verification, then we would also know that there cannot be a proof of this at all. Okay, it cannot be true at all. And this is actually something we're eventually going for, okay, and maybe get to at the end of the lecture to verify, to show that everything that's true has a verification. Okay. Yeah?
So you are normal forms.
Yes. So if you look at it from the point of view of proofs, we have taken instead of all possible proofs, we have restricted them to a certain subset, okay? And this subset is a kind of a normal form of a proof. And this normal form of proof has a property that any proposition, or if you think about it as programs and types, any type occurring in it is a subformula of the thing that you're trying to do, right? So in fact, it's an interesting point, okay? Is it possible that we have an introduction of a connective followed by its elimination? So in other words, could we apply one of these local reductions anywhere in a proof, anywhere in a verification? Okay. So is it possible that we introduce a connective and then eliminate it? Okay. So let's think about it, about the end introduction case. So you want to introduce it, so it looks like this. We have A and B. So we have a verification of A and B to introduce that. And to eliminate it, we want to do that, okay, but the arrows don't match, okay. So we can't introduce a connective and then immediately eliminate it because this is the verification and this is a use, and we don't have a way to go from arbitrary verification to a use, okay. So these normal forms have the property, the verifications have the property that from the programming language point of view, there's no redex in them, okay. There's no place where we apply an elimination to the result of an introduction, okay. So they're normal in that sense, that they cannot be reduced with any of the local reductions. Okay? Other questions or remarks? And if there's something that we can use, we can decompose it into the pieces and then reintroduce it, right? So we can eliminate and reintroduce it, but we cannot introduce and then eliminate the same thing, right?
We can still have like infinite proofs.
Infinite proofs. No, all proofs in the system are finite.
By introducing and eliminating
Well, you can have. Good question. Is that possible?
if we have A and B.
Yeah. No, we cannot introduce and then eliminate.
We can eliminate and then introduce it.
We No, wait. At this point, you can't eliminate anymore. So you can't build these chains. Introducing it. There's another way to get sort of arbitrarily complex proofs, but maybe when I get to the sequence calculus, we can talk about that. Okay, so does this notion make sense? Yeah, question?
I understood the restrictions on the arrows to prove terms that are beta normal.
Yeah.
The restriction of the arrow changing on atoms would have to be beta normal.
That's right. Exactly. So if you know that terminology already, the restriction on the arrows, okay, forgetting about this whole for the moment, that they're beta normal because we cannot introduce and then eliminate anything. The restriction of this to be atomic, okay, means that it's also eta long. Okay. So that's the connection to ordinary lambda calculus theory. Okay, so let's see. So the next thing we want to do is we want to prove, okay, so that's our goal, that if something is true, so it's any proof at all, then it has a verification, right? So you don't want things to be provable that don't have verifications, because that would basically mean that our notion of meaning is no good, okay? So the question is how to do that, okay? So this is actually goes back way back to Gensen in 1935. So in this very seminal paper from Gensen 35, he introduces the calculus of natural deduction and basically said, I want to show that my logic is consistent. And he wanted to show essentially that you cannot prove that the contradiction, okay? You cannot prove that. That means the consistency of a logic means you cannot derive a contradiction from it, right? So that was his goal. Now, actually, let's write down the rules for that just so we can follow Gensen's sort of motivation, okay? What is the up arrow rule for bottom? What's the introduction rule for falsehood? There is no bottom up arrow rule. And what's the elimination rule? Anybody remember? Bottom, you can infer anything. So now we just have to put arrows on. Do that. What's the arrow on bottom here? Down, because something we must be able to use because we apply the elimination to it. And what's the arrow on C? Up. It has to be an up arrow. Okay. Question, why couldn't it be a down arrow? Right. So the way we see that it should be up arrow, if we believe this, then we can see that it's a null array disjunction. So there's no branches here, and you get a verification of C. But here it's very easy to see that it has to be up arrow. It can't be down arrow. Why? That would destroy our whole program. You can use it infinitely many times. That's not so problematic. The problematic is that we want our proofs to consist only of subformulas of what we're trying to prove. If you get a contradiction, you can then use anything from there. That formula may not be contained in what we're trying to prove originally at all. So it would destroy the subformular property and would destroy the compositionality of our definition of meaning. So it has to be like this. Okay, so now, Gensen wanted to prove that we cannot show bottom is not true. So we cannot derive a contradiction. So what he wanted to do was basically that. He didn't quite say it that way. But if there's no verification of it, so if everything that's true has a verification, then there would have to be a verification of it. And now, why is there no verification of falsehood? There's no rule. There's no rule. We can immediately see, we can look at all the rules, and no rule applies. Okay? This rule doesn't apply, by the way, because the logical constant truth and false are not considered atomic, right? These are other propositions which are uninterpreted. So to get this, no rule applies, and therefore it can't be derived. So he brought down the consistency of his logic all the way down to the question whether everything that's true in the system of natural deduction has actually verification. See that? Yeah?
We have to check the two oral rules.
Say what?
We have to check the oral limb and bottom limb rules.
Oh, but you cannot apply that rule because we don't have an assumption.
But what in the case if you have true, then you may use the or limb thing with true or true.
If you have true, what do you mean by true?
If we also, how are the rules for the connective true?
Yeah.
For the top.
Right.
If you do them in the wrong way, then...
No, but there's many verifications of this. There's many verifications of that, actually. There's probably, well, two natural ones. But you still don't have license to use it. We don't have it with a down arrow. Okay?
Okay, but so to answer why we don't have true with the down arrow, what are the rules for true?
Okay, the rules for true, very good question. Okay. So what's true or introduction? Introduction, right? True is true. Okay? It's a nullary case of conjunction. So instead of two premises, we have zero premise. Okay? How do we annotate this with arrows? Has to be a verification, right? Because it's an introduction rule. Now, what is the elimination rule for true? It's a nullary form of conjunction. So instead of two elimination rules, we have zero. And so there is no top-down rule. And also no top elimination rule. Okay. All right. So, so he kind of broke. Yeah.
I'm looking at the bottom elimination rule.
Yeah.
And so if we're saying that all to have verification, you need to use some subformulas.
Yeah.
Bottom is the subformula of C.
That's correct.
So I'm a little confused there.
Okay. So the point is that what happens is doing the proof. You're in a situation like this. If you're trying to find a verification of some A, we have some assumptions B1 through Bn. Okay? We're trying to go this way. And in this kind of a proof, you can use subformulas of A or subformulas of B1 through Bn. Okay? Because if we're trying to set out and we're trying to find some A without any assumptions, okay, then any assumption that we introduce will already be a subformula of A. Right? Because if you look at the rules that introduce assumptions, here assumptions get introduced. That's a subformula of this. Inductively, that was a subformula of what we were trying to prove. Here, we're trying to prove A implies B, so the assumption we make is a subformula of what you're trying to prove. So there's a proof hiding here that I'm not doing relying on intuition, that if you try to prove something closed that doesn't from no assumptions, then anything occurring in that proof will be a subformula of what you're trying to prove. And it comes down inductively, if you have these assumptions and you're trying to prove that, then anything in this proof, if you find of a verification of A, will be a subformula either of A or one of the B1s or Bn's. Okay. Other questions? Okay, so come back to Gensen. So his problem now was, he wants to show that if something has a proof, then it has a verification, because then he knows that because bottom has no verification, because no rules apply, his logic is consistent, right? That was very important at the time, because there was all this thing that started with Russell's paradox, where Frege's logical system was proven to be inconsistent, and everything's on. People were extremely afraid that the system might be inconsistent. And so before Gensen, people didn't have techniques to prove that the logic that they're working with is consistent. Okay. Okay. So he introduced natural deduction, and now in order to prove this theorem that I talked about, he introduces something else called the sequent calculus. And the reason is as follows. It's painful, okay, to always work with a system like this, because when you try to do induction, you always have to consider the possibility that you're working in either direction, either downwards or upwards. When you do an induction over the structure of a proof, which is what he wanted to do essentially, you always work upwards, right? So you say, if an induction over the structure of the proof works like this, we show it holds at sort of at the top, or as you're doing your proof, you're trying to prove it for a conclusion, and then you have to try to prove the property for the premises. Okay, so you always work in one direction, and in this way, verifications gets constructed in two directions. Okay, so then he said, okay, let's just find another system that's somehow equivalent to this. Should be easy to show, so that all the rules work bottom up, and then we can do induction over the structure of proofs in a much easier way. Okay, so. Actually, I should have left that up, but so instead of having B1 down, Bn down, A up, okay. What I did, let's put this on one line, okay. So we have B1, Bn, and put the conclusion on the right-hand side, okay. And this is different from the turnstile notation for this. So the turnstile notation for this would be B1, Bn, turnstile A. And I explain how this will be different when we get to the rules. Okay. So even with the turnstile notation, okay, the elimination rule looks like this. Gamma A and B, gamma A, right? Okay, so that's not what we want. So we need a different form. Even though it superficially looks the same with some things on the left-hand side and a conclusion on the right-hand side, we have to change the rules in order to get our goal that all the rules decompose propositions bottom up. Okay, so that's no good. So turnstile doesn't do it, right? It's still better than this because things are localized into one single hypothetical judgment, but it doesn't decompose the propositions just bottom up. Okay, so pictorially, here's the idea. Okay, so think about, we have a proof, we have some kind of verification of A, and we use introduction rules going this way. And then we have some assumptions here that we can use. And then we use elimination rule going downwards. And they meet at the middle at this kind of coercion. Right? That's the picture you should have in mind. Introduction rule goes up, elimination rules go down. Okay. So now we want to turn this into a form where all the rules are going bottom up. So the way we do that is we leave this line here. Okay. So that line is going to be the same. And the introduction rules are going to stay the same. Okay, so these are called right rules, which should be essentially the same as the introduction rules. Okay, so the right rules work on this proposition here. Okay. And the introduction rules already work bottom up, so we keep those because they're already going the right direction. But instead of going downwards, we flip this thing over, okay, and have left rules, which are the inverse, okay, of the elimination rules, going bottom up, okay. And instead of this coercion, they meet at a place where there's nothing above, and this is called the identity rule, okay. And they meet at that identity rule, so that's the idea, okay. So we're taking the rules we already have for verifications, okay. So this is natural deduction. And this is a sequent calculus. Okay. So now we can systematically write down all the rules for the sequent calculus, and we don't have to really think, because they follow just from this picture. Okay. So we should do it, though. So we'll start with conjunction. If you sum assumptions gamma and A and B, what should be the premises of the right rule for conjunction? Well, it's the same, right? We keep the introduction rule, so it's just from gamma we can prove A, and from gamma we can prove B. So that's the right rule. Okay, so for the left rule, we assume that we have A and B, and we're trying to prove C, and this is, okay, so what is the left rule for conjunction that corresponds to our picture? So take the elimination rule that's up there, the first elimination, we'll flip it over and put it on the left-hand side of the arrow. So what does the premise look like? Yeah? Okay, very important. Okay, very good insight. So, so first, I was going to write this, and maybe actually Charlie will do this later today. Okay, but if we just get A, that's actually not enough. We might have to use another AND elimination to get the second component out. So we have to keep this around. So we might need to use it again. Okay. And then there's a second elimination, or a second left rule, which extracts a second component. Okay. All right. Does that make sense? We're just working bottom up now. And so you see the difference to the turnstile. With the turnstile, the only way we use something from the left is move it to the right in the hypothesis rule when we use a hypothesis. And here we actually focus down on something on the left, and we apply the elimination rule to it essentially by the inverse of the elimination rule. Okay, by taking the elimination rule and inverting it. Okay. Okay, let's do implication. What's the right rule for implication? Yeah? Yeah. By the way, I should point out that even though I write this here as the rightmost thing, because I don't care about the order of the assumption, it could be anywhere, right? So actually, Gensen was even more particular than that. He said, well, it's always the rightmost thing, and then he had an explicit rule to exchange two things. Okay. So then before you apply that rule, you have to move it into the right place. Okay. So today we take a more relaxed attitude towards these sequence. Okay. By saying that underneath we can do that quietly. We don't have to be explicit about it. Okay. Okay, so the question now is, what's the left rule? Implication left. Okay, so we have to look at how we use, right? Because the right rules always have to do with when this thing is with an up arrow, when we use a verification rule. And the left rule always has to deal with a down arrow, because we're eliminating something. So now we have to look at the implication elimination rule to see what the left rule would be. Okay? The picture breaks down a little bit here, right? Because there's actually a side proof of an elimination, which is another introduction. So let's see, what would it be? Anyone take a shot at it? How many premises are there going to be? How many things do we need there? It has to be two premises, right? Because this thing involves a proof of A and a use of B. There's going to be two premises. In one premise, we're going to be allowed to use B. Okay, what does it mean to use B? It means to be on the left, right, of the turnstile. So somewhere here, we're going to be allowed to use B to prove C. Okay, and what do we do in the other premise? We should be able to get a proof of A. And that's with an up arrow, so that's going to be on the right. Okay, so I left some space here strategically because A implies B, you mean? Yeah. So we might need to use this again. Okay. We might need to use the implication many times. So we have to keep it around. Okay. So at this point, there's usually objection. Okay. By somebody who's following along and says, okay, it doesn't really make sense. We don't really need this implication anymore because we already have something stronger, right? So why would we still need A implies B? Okay. Okay. So now the observation is the following. If you remove this assumption A implies B, okay, you can still prove everything in the sequent calculus that has a verification. But you cannot replicate every proof that somebody gave you. Okay. We really want to establish a very close relationship between verifications up there and the sequent calculus. So if somebody redundantly used this more than once, okay, we want to be able to use it redundantly as well. Okay. Then there's a second step that we want to make, which we'll make tomorrow, okay, which is that let's look at these sequent calculus rules, and from the proof search perspective, there's still a lot of redundancies. Let's try to eliminate some of these redundancies. Okay, so today our job is just to show, to get this picture to be as accurate as we can. So try to really translate verifications to sequent proofs. Okay, anything that one might do by building a verification should have an image in the sequent calculus. Okay, because at the moment our goal is foundational, right? We want to prove that you cannot prove a contradiction. We want to verify that. Let's see. Oh, I started at 9:30 today, right? That scared me for a second there. Okay. All right. Okay. So we should have more rules. So what are the rules for disjunction? On the right. Okay, it's too easy, right? Maybe I should just let you give the rest of the lecture. Okay. Because now we're just, doing what we mapped out, right? So what are the right rules for disjunction? Should be trivial. Right. It's a possibility that we just get A, or we could just get B. Interesting, not. What's the left rule for disjunction? We know there should be one, right? Because there's one elimination rule for disjunction. Okay? Anyone want to take a shot at what the premises are? Gamma A proves C. Okay? And gamma B proves C. Okay, I left some room there because we keep all the assumptions, right? Just because the verification might actually use it again. Even though we'll know tomorrow that these are redundant, right? We don't really need that. Because already A is stronger than A or B, so there's no point in keeping A or B around, except the fact that we want to model every verification, and if somebody distinguished cases twice in a redundant way, we should be able to model that. Okay? All right, let's do falsehood, and that's particularly important because that's Skenson's starting point. What are the right rules for bottom? Okay, no bottom right. What is the bottom left rule? What's the bottom left rule? I'm already done writing it. That's it, right? Okay. You can see that either by translating the elimination rule up there, or you can see it by seeing the nullary case of disjunction, right? We have two branches here, and since there's no components of this, there's nothing here. So if you've reached a contradiction, you're done with your proof, is what this says. Okay? Do we have all the rules for the connectors so far? Yeah? Right, so now we have to worry about structural rules. So if you want to model verification, what kind of rule do we need? We're not quite done yet. Hmm? Yeah, you still need that coercion that goes from down to up. What would that look like? Okay. Anything on which is we can use with the down arrow, okay, comes to the left-hand side. And the thing we're trying to prove comes on up arrow on the right-hand side. And this is called the identity rule, which is this one where the two meet, right? So the left rules, the inverse of the elimination rules, have to meet, the decomposition of the right-hand sides, and they have to meet when you have the same proposition P here. Okay? That exactly corresponds to this rule over there. Okay? And in fact, you can prove those theorems, right? I actually don't think I will go through the trouble, but you can you can look those up. You can show how these things are related by proving an appropriate inductive theorem. It's not completely trivial. And the reason it's not completely trivial because of this change of direction you have on the natural reduction side. So there's some interest to just sort of proof engineering to do this properly. But since we designed it sort of very carefully, it should be clear that we should be able to prove that. Okay. So if you want to model verifications, this is all we have. Okay. Now, if you want to model arbitrary proofs, we need something more. Okay. So there's going to be two more rules, so to speak, or one relaxation of a rule. So the one relaxation is this. If you can use A, you can prove A. Okay, so that would be the identity at a larger proposition A. Okay. So that basically relaxes this restriction we have in verifications, and we can only use something when it's atomic. Okay, we did that because the meaning of the connectors was defined by the introduction rules. So at some point we should have to introduce it. And if we do that, then this A actually never gets introduced because we have it as an assumption. Okay, so allowing this relaxes our restriction on what a verification is. Okay. Hmm? Right. So what we want to show is that this rule, okay, is admissible in this calculus. Okay. So if you want to talk about it this way, then we would say we don't really need this rule. We only need the identity at atomic propositions, and that's because we can't break those down further. Okay. Okay. So we still cannot represent arbitrary proofs. Okay. The reason we can't send arbitrary proofs is because we very carefully engineered it so we can only represent verifications, right? Okay. So the question is, can we modify this system that we have up here to permit arbitrary proofs? Okay. So the question is there some simple way to do that? Yeah? Right. So allow arbitrary proofs, what you can say is whenever we have a verification of A, we can use it. Okay? And of course you would allow this to have to be there for arbitrary formulas. Okay? So if you do this and we have the opposite, that basically means you can go back and forth between verifications and uses arbitrarily. Okay? So this distinction that we made in the rules is completely null and void because we can go back and forth whenever we need. So we just recover the ordinary provability with truth, okay? Except there will be a couple of extra rules sprinkled in, okay? We go back and forth wherever we need to. Does that make sense? Okay? Because whenever we want to eliminate something that we have a verification of, okay, we just flip the arrow and then we use it, okay? So basically, we eliminate the distinction between verification and uses if we do that. Okay. So we don't want to do that if we want to have verification, and we don't want to do that in the for arbitrary A. But if you want to capture arbitrary proofs, we can do that by just having those two rules. Okay. So what would be the analog of this rule? Okay, if we think about the sequent calculus. What would be the analog of that? The cut, okay, so what does it look like?
A on the right side,
And then prove A. Yeah.
and you have A on the left side.
as a rule, but I want to show that we can always do that in some sense. Okay. So the cut rule represents this in the following way, right? In the premise here, we have a proof of A on the right-hand side. So this premise corresponds to this. Okay. Now this allows us to use A, so we have to put A on the left. But what's in the conclusion of that? Well, we don't know what we're trying to prove overall, but in this overall proof, we're going to use A. So here we just name, okay, let's call this B. Okay. And then at the end, we have a proof that doesn't use the assumption A, because I have a verification of it that should be okay. That's our conclusion here. Okay. So this corresponds to the general form of this rule, and the cut rule corresponds to the general form of that rule. Okay. All right. So if we have these two principles, we can take arbitrary proofs over there, and we can construct into proofs over here. Okay. Let's see. Okay. I wanted to make a remark about these rules. Okay. Because there's several things that are very nice about sequent calculus rules. Okay. And this is one of the reasons why many people sometimes even start with the sequent calculus when you define the logic. They don't even start with natural deduction. Okay. The nice thing is that the rules have a very uniform quality to them. Okay, so when you look at natural deduction, the and elimination rules just get rid of the conjunction and give you the pieces. For the or elimination rule, you need to do this weird thing where you have the C that you're trying to prove and you put it at the bottom, right? So the two rules for and elimination and for or elimination are very different forms of rules. They look very, very different. Okay. Now here they actually look quite similar. Okay. You focus in on something on the left, you break it down, extract a piece. Focus on the left, extract it down. Look at the left. Okay, extract a piece here, extract a piece there. Okay. So in some sense, the rules are very uniform at this point, right? The left and right rules of the sequent calculus are more uniform than the rules of natural deduction. Okay. Now, the reason to do natural deduction has more to do with programming. Okay. Because it really corresponds to systems of functional programming in a very direct way, because we gave this Curry-Howard interpretation of terms. Okay. If you look at the sequent calculus and you give a Curry-Howard interpretation, it's a much more complicated matter. Okay. It's not very convenient to program with the sequent calculus terms. Okay. So a natural deduction is very good if you want to relate this to functional programming. If you want to present a logic in and of itself and prove properties of it, it's much more convenient to have the sequent calculus. Okay. For two reasons. First, the rules are very uniform. And secondly, all the rules work bottom up, which gives you a very easy handle to prove properties of the logic that you don't have in natural deduction. I mean, it's possible, of course. It's just more complicated. Okay. So now we can come back to Genson's original issue, right? So if we know that these sequent calculus rules are complete, and these two things are admissible in the sense that we don't really need them, okay, again, we can see that the logic is consistent, right? And we can derive some other properties as well. So let's just derive some other properties. So for example, I know this cannot be proven, right, in the sequent calculus without those two rules, because right, it doesn't have subformulas, but you just look at the rules. Which rule could it be that we apply? There aren't any. Right? So immediately we know this cannot be proven. Here's another thing. If you have A or B, I claim if A or B, then either we can prove A or we can prove B. Okay, how do we argue that? Yeah, we just look at the rules, okay? Which rules could apply here? Well, no left rule at all, because we have no assumptions, right? What are the right rules for disjunction? Well, there's just two right rules, this one and this one. If it was this rule that was applied to infer that, right, then we have A. If it was this rule, then we know B, okay? So now, why is it the case that we cannot prove A or not A? Okay. Well, by the same argument as before, it must either be A or it must be that. Well, it couldn't possibly be A because we have no rule for that. Okay, so it must have been A not A. Well, there's only one rule for that. And at this point, no rules apply. There's no right rule for bottom, and there's no generic left rule for A. So, cannot be proven. Okay. So the law of excluded middle cannot be proven. Okay. Now you can look at some of these interaction laws that these false De Morgan laws that we looked at in the last assignment, and you can verify using these techniques that they cannot be proven in general. Okay. Now the important property here is that I'm trying to prove these without regard to what A or B is. Right. The question here is there a proof in general for arbitrary A that A or not A. But for specific propositions, we may still be able to prove that. Right. So. Can somebody give me an example of a specific proposition where we can prove A or not A? Yep. Okay. True or not true. Well, how do we prove that? We use the first or right rule to prove true, and then we use the top right rule to conclude that. So for true, it's the case that the law of excluded middle holds, right? So in fact, there's infinitely propositions for which this holds, okay? Infinitely many propositions, but it doesn't hold in general. So if you want to prove A or not A, you need to know something about A, right? And I've just shown you that you need to know something about A because if you don't, if this is just an unknown atom, then you get stuck at this point, okay? All right, so now, in some sense, there is some proving to do, but we have broken down the whole problem of proving that the logic is consistent to essentially showing that we don't need this rule, okay, that this rule is always admissible, because the difference between truth and verification is the presence or absence of this particular rule, okay. So if we can show that this rule is really not needed, then we're in good shape. So what we want to be able to prove now is that if you have a sequent calculus proof with these rules of this, and we have a sequent calculus proof of that, then there is already sequent calculus proof of this thing over here. Now, it should look familiar somewhat. If you put a turnstile here, what is that? No, not implication elimination. If I put a turnstile here, and a turnstile here, and a turnstile here, what is this? No, not weakening. What did you say? No, because there's no connection, no implication. It's not that. It's substitution. Okay? Remember the rule for substitution said if you have gamma m colon A, x colon A, turnstile n colon B, then in gamma m for x and n colon B, right? It's substitution. If you forget about the proof term, right, it's just that. Okay, but we have to keep in mind that there's a difference between natural deduction and sequent calculus. So the fact that the rules will look similar, they still have a very different interpretation. Okay, interpretation here has to be if you have a verification of A, then we can use A. By the way, there's also duality here between this identity and this cut rule. Okay, this identity rule says if we can use A, we have a verification of A. This rule says that if we can use A, now, if you have a verification on A, then we can use it. Okay. So basically, with these two rules, it means we can go back and use force between verification and uses, which is also exactly what those two rules say. Okay. So the question now is how do we prove it? And of course, in 10 minutes, I can't give you the proof, but I can at least sketch to you how this works. And this was Genson's real accomplishment to prove this theorem, or a version of this theorem. Okay, so the theorem is that if in the sequent calculus, without the rule of cut, of course, gamma arrow C. Okay, so how do we structure the proof? Okay, so I mean the whole point of Gensen's reformulation of natural reduction sequence calculus was that we can analyze the structure of these proofs. So let's call this proof D and this proof E. So what we do is we analyze the structure of the two proofs and see if we can simplify things. Okay? And eventually we'll have to worry about some kind of proper induction measure. Okay? But let's just see what happens in various cases. All right. Let's try to take some simple cases. Let's say D has this form. Actually, D is arbitrary. And E was the identity. So E looks like gamma, comma A, arrow A. Okay. Okay, so what do we do in that case? Okay, so what does the conclusion look like? Well, the conclusion says from gamma we can prove C, but C is equal to A by the identity, so we'll just take A. This proof, right, to get our conclusion. We can just reuse that for that, because if this is the identity, A and C must be equal. So easy case. If the left-hand side is the identity, equally easy. Okay, so if it's identity, there's nothing interesting going on in this proof. Okay, so let's look at a more complicated case. Okay, let's say the proof D consists of two subproofs, A1 and A2, which is a proof of A1 and a proof of A2. And the proof E uses the extracts the left component. Okay? And that's E. So this proof is called a D1. Let's call this D2, and let's call this E1 because it's the first component. Okay. So how can we argue? Okay. So what we have to show at the bottom is that from gamma we can prove C. So we have to somehow argue that we can simplify things here. Yeah? Okay. So we have A1 here, and we have A1 here. So we should be able to do a cut on this one and this one. Okay? Okay, but okay, so we need to weaken that here. That actually doesn't work, unfortunately, so we need a different idea. The problem is that if you want to cut this with this, okay, this thing is still in the way. Weakening that will get us into trouble. Okay, weakening, I mean changing this derivation to add A1 and A2 everywhere. So I don't want to do that because that gets us into trouble. Okay, so the question is, in this proof here, we're going to get rid of A1 and of the conjunction. Okay, can we get rid of the conjunction first? How could we get rid of the conjunction? Hmm? We could use the other left group N, but the conjunction it still copies it. Then you can eliminate it. Yeah, that's not. I believe you can prove it that way, but that's not the way I want to do it because then I have to change this, massage this whole proof somehow in a complicated way. I want to look for a more local way of doing this. Okay, so the idea is to take the following. We somehow apply the quote-unquote induction hypothesis, which we don't know yet, with all of D in this premise. Okay? And to cut out the conjunction first. Okay? Okay, so we have to think about what's getting smaller. So let's say we could get the derivation of gamma A1 proves C by induction hypothesis on all of D and E1. Right? So D stays the same, E gets smaller. So maybe that's okay, because originally we had a cut, or we wanted to prove it for D and E. So we keep D the same, make E smaller. Seems all right. Okay? Because something gets smaller, and the other thing stays the same. Maybe we're doing okay. And now we want to apply a cut between D1 and this thing here. Okay, so that would give us gamma arrow C by induction hypothesis on D1, and let's call this F1 and F1. Okay. Okay, now that's problematic. Okay, because even though D1 is a subformula, a subproof, right? D1 is smaller than D. F1, we have no idea what that is. It could be arbitrarily large because it's a result from our first appeal to the induction hypothesis. Okay, so the idea that we just reduce the structure of both proofs doesn't quite work. Okay, we need something slightly more insightful. So, what is smaller here? Yeah? The cut formula, right? Because this is a cut on the formula A1 and A2 that we apply here. At this point, okay, we do a cut on A1, which is a subformula. Okay, so this is induction hypothesis on A1 and A2, which stays the same, D, which stays the same, and E, which gets smaller. Okay, this is induction hypothesis on A1, which is smaller, D1, which happens to be smaller, and F1, which is larger. Okay. Okay, so what that means is that, well, I mean, there's many cases to consider, of course, but what you end up in the end is that noticing that the following structure works. You either reduce one of the two proofs by making it smaller, okay, so because we keep one the same and make the other one smaller, okay, and then the cut formula also stays the same. You're cutting out the same cut formula. Or we reduce the size of the cut formula, okay, and then the other proofs can be arbitrary. It doesn't matter how big they are. Okay. That's called a nested induction, or a lexicographic induction according to a lexicographic ordering. Okay. So lexicographic in the sense that if you have a pair A, D, E, where these two happen at the same time, is less than the pair A prime and D prime and E prime, okay? Sort of like in the dictionary ordering. So if either A is strictly less than A prime, so this is strictly less than that, then the D and E don't matter. Or A is equal to A prime, and one of two things, either D equals D prime and E is less than E prime, oops, or E is equal to E prime and D is less than D prime. Okay. So that's called a nested induction or lexicographic ordering, like I said, and you need to convince yourself that this is a well-founded ordering, and in fact it is. Eventually you have to bottom out, because the formula can only get smaller sort of finitely many times, because we start with a finite formula to begin with. If the formula stays the same, eventually we'll have to make the formula smaller, because these proofs sort of have to, in lockstep, somehow go, not in lockstep, maybe alternatingly, but they always get smaller while the other one stays the same. Does that make sense? Yeah? We don't have a rule of contraction, but it's an admissible cut.
So what if you have like gamma A, comma A implies D,
Yeah.
and then you do a cut, and then you first do contraction and then do a cut?
No, we don't have contraction as a rule.
Oh, so you don't.
No, and we don't need it as a rule because I'm keeping around a copy of every formula along the way as I go. Okay. So another way to organize things is to get rid of this formula, okay, and have a rule of contraction which looks like this. So if I have one assumption A, then I'm allowed to copy it. Okay. So unfortunately, if you have an explicit rule of contraction, the proof that cut elimination holds is much harder. Okay. So instead of doing that, the way we're going to, the way I did it here is that whenever you apply left rule, you keep the copy around. Okay. And then it's very easy. Well, not very easy, but you see what kind of induction you need to prove that. Okay. Now, when we prove these properties by induction, we actually fix the logic that we're working with. Yeah? Did you have a question? Okay. So in other words, a lot of the things that we did so far were really centered around the individual connectives, and we didn't look at the rest of the logic. It was very important that the rules were pure, so that introduction rules for each connective only refer to judgment and no other propositions, right? So that we can construct the logic, the various connectives completely independently. Now, if you want to prove the admissibility of cut, okay, like this property here, we need to close up our logic and say, now we're done. We have all the connectives. Let's make sure that for this logic, okay, this principle holds. Okay. So at that point, you have to say our logic with respect to the following connectives is actually consistent. Okay. So if I now add a new connective, like a new judgment or even a new connective to the logic, like for example, if I want to have a monad, right, then I kind of have to redo that proof. Now it turns out you can organize this proof in such a way that it's fairly modular, so you don't have to worry too much about adding new things. And that kind of modularity sort of derives from the fact that the left and right rules are modular. Okay? So the left and right rules only refer to the connectives you're defining and nothing else. Okay. But that's more, it's not a formal statement about the cut elimination, the proof of cut elimination as far as I know, but it's an empirical observation. Okay? That you get the benefits for defining your system very carefully so that all the connectors are orthogonal leads to the fact that your proof of cut elimination and other properties of the logic is modular as well. Okay. I'm a little over time, but I'll still answer a few questions. Yeah?
This via cut elimination, is that indeed easier than just using Tate's method directly on the natural deduction system?
Yes.
That's just your personal opinion, or it's really shorter if you write it down?
No, if you think about the proof theoretic strength of what you need, if you really want to classify Tate's method, it's very significantly harder in some kind of formal sense than this cut elimination argument.
Okay, but the problem of this argument is that it does not extend to second order, whereas Tate's method does.
That's right.
Okay. So eventually it pays off. The Tate's method.
What do you mean by pays off? When we have a new logic with new properties, we need new methods. Right?
Yeah, okay.
Yeah. But actually, it's not so easy to prove this with Tate's method if you have disjunction. I mean, it's possible, of course. But if you just have implication and conjunction, Tate's method is quite simple and straightforward. If you add disjunction and falsehood, it becomes complicated. I don't know if you've ever done that proof in complete detail, but it's complicated.
Yeah, I did it for another variant. I know the problem.
Yeah. Anyway, so the cut elimination proof actually is just a very simple structural induction nested. Okay, so it's very easy to mechanize. So I've mechanized this proof in a 12 logical framework, and it's a fairly simple thing to use. Other questions? Okay, so then tomorrow I'll tell you more about how to eliminate. So the sequence calculus here, and also again, since we're designing model what you can do in natural deduction. And I hope you saw that what it does, it takes the steps that you can take in natural deduction and represents each step during proof construction as a bottom-up rule, okay, in a new formal system, which is the sequence calculus. But of course, the system is quite redundant, the way I've written it down, which is very convenient for the purpose of proving these things, but it's not convenient for actually constructing proofs. So we'll analyze some of these redundancies and try to get a calculus that's much more streamlined, okay, and that'll be a subject of tomorrow's lecture. Okay, thank you.